Okay, so review the concept of momentum. Momentum is a quantity that reflects the vector amount of motion. It's equal to the product of an object's mass and velocity, so its units are kilograms times meters per second. This ends up being equivalent to a Newton second as well. So that's our definition of momentum. Now when momentum changes, remember the symbol delta is a change, so that's final minus initial. That'll be a mass times a final velocity, and I've got to be picky about my vector directions here, minus a mass times an initial velocity. Now we can factor out mass, and then I can divide and multiply by time without changing anything. The reason for that is this ratio here is the acceleration. At least when the acceleration is constant, that's the acceleration. And the product of mass and acceleration is, of course, the net force according to Newton's second law. So that's net force. Let me draw it again because that was a bit untidy. That's net force with an arrow on it to signify a vector. So it's net force times time. All right, so momentum change then is equal to the product of force and time. That actually has another name. That's impulse. So impulse is the product of net force and time, is the momentum change, is the mass times the final velocity minus the initial velocity. This is known as the impulse momentum theorem. And largely, these are just reformulations of Newton's second law, or this is really a reformulation of Newton's second law, and it's not intrinsically useful on its own, except insofar as the collision problem is concerned. For collisions, if they happen in a closed system, and the closed system just means they're cut off from the outside world, and therefore the only forces that act on them are internal forces. One way to get that is on a frictionless surface, because then the weight, which is an external force, is just balanced by the normal force from the frictionless surface, and therefore the only unbalanced forces within the system are the action-reaction pair. So in the collision, these two forces will be equal and opposite. These should, strictly speaking, have little vector arrows on top of them. Those forces, because they're contact forces, are an action-reaction pair. Let's tidy that up a little bit. That's a bit messy here. It's important to get it right. So I'm just putting what's known as a system boundary around here and saying there's no effect from the outside world on this system. And then I'm saying that there's two forces in here. There's going to be an action force, and there's going to be a reaction force, and those two are equal and opposite. And I'm just going to drop the vector arrow because I can't do those neatly enough. Now, because those forces are equal and opposite, if we multiply by time, and here I'll put the vector arrow back in down here. If we multiply by time, it's still equal and opposite. But of course, the product of force and time is the momentum change. This will be the momentum change of the first object, vector, and this is the momentum change of the second object. So what I've shown is, if you have a closed system, then the only forces are contact forces, and they're governed by Newton's third law. And therefore, equal and opposite forces implies equal and opposite impulses, implies equal and opposite momentum changes. Now, what does it mean to say momentum change is equal and opposite? Well, that means that if an object loses a certain amount of momentum, so one object loses a certain amount, then the other object must gain exactly the same amount. So it's equal but opposite. So one gains, the other must lose. So then, in that case, the total initial momentum will equal the total final momentum. And there's a couple of ways to write that. Here's the way you write it first. m1v1 plus m2v2 at the beginning equals m1v1 plus m2v2 at the end. A little bit later, we use sigma notation. The sum of the momentum initial vectors equals the sum of the momentum final vectors. And that's the more sophisticated way of writing it. So this result was proved using the impulse momentum theorem. And for my money, it's really the only useful application of impulse and momentum. Here's a typical momentum problem. We've got a 1,000-kilogram car. Okay, so here's the car, 1,000 kilograms, and it's moving at 8 meters per second. And it runs into an 800-kilogram motorcycle. After the crash, the motorcycle is moving at 5 meters per second. Now, the motorcycle was stationary originally, so it was at rest. We want to know how fast is the car moving. And we want to find the amount of kinetic energy that was lost in the collision. All right, so to find how fast the car was moving, we'll apply the principle of momentum conservation, which says sum of the initial momentum equals sum of the final momenta. So initially, the motorcycle has 0, and the car has 1,000 kilograms times 8 meters per second. That's 8,000 units of momentum. At the end, the speed of the car is unknown, so we introduce the variable v. And here, the 800 kilogram motorcycle is moving at 5 meters per second. So here we've got units of kilogram meters per second, and I dropped the units just for simplicity. So this is 8,000, this is 4,000. Bring it over, divide by 1,000, and you isolate the unknown variable v. So we see that the car is moving at 4 meters per second in the positive direction after the collision. Now, had we gotten a negative answer, that would have told us the direction of the car. So let's just note that this was positive, and that positive has significance. Really, this is a vector equation, and we should indicate the directions that the objects are moving using positive and negative signs. But everything was moving to the positive or right direction, so there were no negatives here. Next, let's find the kinetic energy lost in the collision. We'll apply the work energy theorem, which says initial mechanical energy plus the work done by non-conservative forces equals final mechanical energy. For our mechanical energy here, we just have kinetic energy. At the beginning, there's just the car that has kinetic energy. At the end, both of them have kinetic energy. Now, the car initially has more kinetic energy than it has at the end. So, kinetic energy is 1/2 mv squared. We know the initial speed is 8 meters per second. Final kinetic energy in the car, well, it's now moving. We just found its speed. It's moving at 4 meters per second. And the bike was given to be moving at 5 meters per second. So this has been reduced to a calculation. We can find the amount of kinetic energy that was lost. This is also the amount, so it's the kinetic energy that was lost. It was transformed to other forms of energy because, of course, the energy of the universe is conserved, usually to thermal energy, okay, in the case of collisions. Okay, now let's look at a two-dimensional collision. So we are in top view here, looking at this from above. So this could be, 2 curling rocks or 2 billiard balls. Here's a before picture, here's an after picture. Now in this case, we're going to apply momentum conservation to the x direction and also to the y direction. So in the x direction, by x and y, here's my coordinate system here, we can see we've got a component here. So the 2 kilogram mass, the x component is going to be the cosine component, 3 cos 50 meters per second. The 5 kilogram has no x component. It's just going in the y direction. Similarly, after the collision, the 2 kilogram has no horizontal component. And for the 5 kilogram, we'll introduce a variable Vx. So those terms are just wiped out. So this equation can be solved for Vx. Next, the initial y component will equal the final y component of momentum. And so here we've got the 2 kilograms, and its y component is upwards 3 sine 50. Then the 5 kilograms is downwards 1 meter per second in the y direction. Same thing, downwards y direction for the 2 kilogram. And let's introduce the variable Vy for the unknown y speed. Now we could solve those two equations for Vx and Vy, and then we can just find their resultant to find the final speed. Now it's also possible to use whole vector techniques, and here what we're going to do is we're going to add up all the initial momentum vectors and the final momentum vectors and set them equal to each other. So here at the beginning, before this collision, it's sort of an oblique collision. This mass is going to strike the 10 kilogram and then they're going to fly apart at a certain angle. Our initial momentum is 2 times 8 is 16 units of momentum. So that's our initial momentum. For the final momentum, well, here we've got 2 kilograms going at 6.7 meters per second. That's 13.4 units of momentum. And the momentum vector is in the same direction as the velocity vector, so it's also 10 degrees relative to the horizontal. And this one has an unknown speed, so its momentum will just be 10 times v. Now what the momentum conservation law tells us, though, is the total initial momentum, which is 16, must equal the total final momentum, which is the sum of these two vectors. Now, we add vectors using a head-to-tail technique, so that adding this known momentum and this unknown momentum, we have to get the total initial momentum, which is 16. So we see that we end up having a triangle to solve. That works whenever one of the objects, either before or after, is at rest, and then the 3 vectors have to add together, or rather the final vectors add together to give the sum of the initial vectors. As long as you only have 3 vectors, it will always be a triangle and can be solved in this way. So not that it matters, but you would do this. It's sufficient to be able to set up the triangle, but you would solve this triangle. I'll just remind you of your high school math using the cosine law. So 10v all squared would be a squared plus b squared minus 2ab cosine c. So that could then be solved for v. It's been reduced to a calculation. Now, a little important collision vocabulary. We have 3 types of collisions. We have completely inelastic collisions, elastic collisions, and then partly elastic, or just inelastic. Now, we'll define those in a minute by showing you a short video, but later on, after the definition, we're going to relate the type of collision to a parameter known as the coefficient of restitution. So this, it turns out, will be a coefficient of restitution of 0. This will be a coefficient of restitution of 1. All right, so after watching that brief video, hopefully now you have these definitions. In an elastic collision, the objects bounce off, and there's no thermal energy created. Momentum is conserved, and so is kinetic energy. In completely inelastic collisions, it's where they stick together. Momentum's conserved, but some kinetic energy is converted to thermal energy. In partly elastic collisions, they bounce off, but there is some thermal energy created. So kinetic energy is not conserved, but momentum is conserved. Now, elastic collisions, nearly elastic collisions, will happen between steel balls. And here's an example of how we might analyze an elastic collision. So here's the before picture, here's the after picture. So momentum conservation, for our initial momentum, 6 times 5, 2 times minus 2. The final momentum, this is a 6 kilogram, this is a 2 kilograms. So we have an expression, it's 6u plus 2v. Now, if we bring the 6u over, this is 30 minus 4, this is 26 on this side. subtract 6u, divide by 2, you can isolate v. Considering next the energy, initial energy plus non-conservative work equals final. If it's an elastic collision, if and only if it's elastic, then this term is 0. In most collisions, it's non-zero because collisions create thermal energy. So for the initial kinetic energy, 1/2 mv squared plus 1/2 mv squared will equal the final kinetic energy squared. Sorry, the final kinetic energy, 1/2 mv squared. Putting in u for the first mass, we get 3u squared. Putting in v for the second mass, we get v squared. So this is a quadratic. Now we can solve this by substituting in this expression for v right here. So we're going to put this in where we saw v. So this was v here. This is our kinetic energy equation. 79 is 3u squared plus v squared. So this is 3u squared plus v squared. Square the bracket. Use the distributive law or FOIL. Add the like terms. Bring the 79 over. You get this equation. Divide by 6. You get this equation. Factor. This is going to be 2 and 1. This is going to be -5 minus 3 to give you plus 15. And you read them off like this. 2u minus 3, u minus 5. If this equals 0, we use the 0 principle. So 2u minus 3 is 0. So u is 3 over 2. This bracket just gives u equals 5. The corresponding solutions, oh, sorry, that's right here. Didn't need that at all. Let's write that more neatly. So this first bracket, 2u minus 3 is 0. That gives the 3 halves. We also have 5. The corresponding v values can be found. However, we see that there are 2 of them. One of them can be rejected, though, because 5 minus 2, that's what it was before the collision. So if they don't collide at all, and then those speeds don't change, that's certainly one way to conserve energy and momentum. So the other case, which is this one and this one, that must be the case where they actually collided. So this is the value that we will select. So that is how we can analyze an elastic collision. Of course, elastic collisions really don't happen. All collisions are inelastic to at least some extent.